This is the third lecture on rigid body dynamics. In the first lecture, we have introduced the rigid body, its degrees of freedom, and the number of constraints. In the second lecture, we have discussed the motion of rigid body, in which we learned that the pure translation is such a motion in which every particle of every constituent of the rigid body undergoes the same linear displacement. When the particles of the rigid body undergoes a motion along a straight line, it is called rectilinear translation, and when they moves on a curved path, it is called curvilinear translation. The translational motion need not be along a straight line always. In period rotation, every particle of the rigid body undergoes the same angular displacement. And in pure rotational motion, every particle of the rigid body executes a circular motion, a circular motion where the center of the circle lies on a straight line called the axis of rotation. And in general, the motion of a rigid body can be looked upon as a combination of a pure translation and a pure rotation. The choice of translation vector and the rotation is not unique. We can, starting from some initial configuration, we can reach to the final configuration via the infinite number of rotation translation combinations. However, it is convenient to look upon the situation as the translation of the center of mass and the rotation about an axis passing through the center of mass. In the last class, we have also proved that the orientational aspect of the rigid body can be taken care of by a orthogonal matrix, which signifies the rotation about a specific axis. In this lecture, we shall mainly consider the few kinematical aspects of rigid body. Firstly, we admit that a rigid body is a system of particles. It is a particular type of system of particles. So, a rigid body is a system of particles. So all the laws of mechanics that we can derive for the system of particles is applicable for a rigid body also. So consider the ith particle of a rigid body with mass mi, position as measured from some suitably chosen coordinate system is Ri, the velocity Vi, momentum Pi is equal to Mi Vi, and the angular momentum Li is equal to Ri cross Pi. Now, this angular momentum is with respect to the origin of the coordinate system chosen. Firstly, mass, total mass is the system is defined as sum of the masses. So if this it comprises of n particles, so this is L. Now, center of mass. If we define center of mass, center of mass coordinate is defined as mr is equal to summation over mi ri, sum over r. Total linear momentum with respect to the from suitably chosen coordinate system, total momentum E is defined as summation over Pi is equal to summation over Mi Vi. And if we differentiate this relation with respect to time, we find that summation over mi vi is equal to m into v. So this is mass times velocity. So this is the total linear momentum of the system of particles can be looked upon as the entire mass is situated at the center of mass, and the center of mass as a whole moves with the velocity v, where v is related to this mv is equal to summation over I mi vi, and if we differentiate once more, we get acceleration of the center of mass as ai is the acceleration. Now the angular momentum. Angular momentum L vector is defined as the summation over I of Li's, and this can be written as linear momentum of the center of mass, that is the r times mv plus the angular momentum of the system with respect to center of mass. So here we have introduced the coordinate system such that this S frame is an inertial frame in which the position is Ri, velocity Vi, momentum Pi, and this is a frame. This is the frame fixed with the Cm, and the position vector with respect to this frame is Ri prime, Vi prime, Pi prime, Li prime, etc. All the quantities are denoted by this is the Cm frame. So in that case, this is the angular momentum of the center of mass. So this is the LCM, and this is L prime angular momentum with respect to the Cm. In this notation, this can be written as P of Cm. These are the few kinematical relations for a rigid body. If we have a continuous mass distribution, then we can define the mass density. That is, if we have a rigid body called continuous charge distribution, then we divide it into small volumes, and then for this, if we want the volume, so the total volume V is decomposed into sum over in volumes, and the mass of this ith volume element delta mi is the mass of the volume element V. If we want to find out the mass density at a point over here, then we pick up the volume element which is over this location, and we calculate the quantity delta mi delta vi with the limit delta vi by v tending to 0. If we go on decreasing delta vi and go on calculating this quantity, we ultimately land up with the mass density over this. And for non-uniform distribution of mass, the rho is different at different points. So for continuous mass distribution, this relation can be written as rho of r dv integrated over v. And then center of mass, the definition of center of mass is mr is equal to integration over v rho of r dv integrated over v. This linear momentum relation becomes integration over this definition of linear momentum, this definition of linear momentum becomes, we use the definition, this one, r cross rho of r v at r dv is the linear angular momentum. So these are the kinematical relations of a rigid body. The relation written in the back color using summation symbol are applicable when we look upon the rigid body as an aggregate of discrete point masses, and when we assume the rigid body or look at the rigid body as a continuous charge distribution, these red color relations hold good. Now we come to some dynamical relations related to rigid body. These are the kinematical relations, and dynamical relation is the relation of, so dynamical relations. Dynamical relation are this: force F, it is the total external force acting on a rigid body is equal to its total rate of change of momentum, valid in any inertial frame. Recall that in deriving this relation we have used Newton's first law and Newton's laws of motion, which are valid in inertial frame, and if the Newton's third law is valid even in its weak form, then the internal force do not appear when we consider the motion of the rigid body as a whole. Recall that the force on the ith particle comprises of two parts. One is the Fi external, and other one is the force on the ith particle due to the jth particle. This is the internal force, and this internal force cancels in pair, so that when we sum over Fi, this part goes to zero, provided Newton's law is valid even in its weak form. And the other one is the relation. The external torque is equal to del L del T. This is valid in any inertial frame, provided Newton's third law is valid when third law is valid in a strong form. Strong form. It is also valid in CM frame. Valid in CM frame. It says that the net external torque acting on the system of particles is equal to dl dt, where L is the total angular momentum of the system of particles. In this case, the internal force, internal force that acts on the body must satisfy Newton's third law in its strong form. Otherwise, if the force on one, F12 and F21 are equal and opposite, but if they are displaced by the, then it will give rise to a couple. Now we shall consider, in this section we shall consider mainly about the rotational aspect of a rigid body. So we shall be very much interested in deriving relation between rotational, kinematical relation between rotational and translational quantities. That is the relation between angular displacement, angular displacement with linear displacement, angular velocity with linear velocity, and angular relation between angular and linear acceleration. Obviously, other quantities will be involved in this relation. First of all, we can differentiate between two types of rotational motion of a rigid body. So, if we call the rotational motion of a rigid body, it is of two kinds. One is the rotational motion about an axis, about a fixed axis. Then, in this case, the system has only 1 degree of freedom, and two, that is, if any 2 points on the rigid body are fixed, then we can assume an axis passing through these 2 points, and the body can at most rotate about an axis passing through these 2 fixed points. Another thing is that rotation about a fixed point. In this case, the degree of freedom is 1, and in this case, degree of freedom is 3, because only 1 point is the body is fixed, and the body rotates about an axis passing through this fixed point. Obviously, if we consider that this is the fixed point within a rigid body, any axis, the body can rotate about this axis, it can rotate about this axis, so there are infinitely many axes that can pass through a fixed point, and people speaks of instantaneous axis of rotation. So one speaks of instantaneous axis of rotation. That is that we may think that at a particular instant of time, this is the axis of rotation. It changes with time and may go to over there. So this is the change of axis of rotation. However, whatever we are going to talk in, what we are going to discuss is valid at a particular instant. Say we have a rigid body. So the relation, first we define relation between linear and angular displacements. So we have an instantaneous axis whose direction of the axis of rotation is given by n cap. So this is an instantaneous direction of axis of rotation. So the rigid body is rotated about this axis. So every particle of the rigid body undergoes the same angular displacement theta. Say we have a rigid body, this is a rigid body, we consider this is the ith particle, and this is the axis, instantaneous axis, and if we choose, this is the position vector, so this is the position vector of the ith particle Ri, This is the position vector of the ith particle, and this is the n cap axis. So this is the n cap axis, and this particle executes a circular motion, and the center of the circle lies over there. If we choose this is O point and this is O prime point, so axis of rotation is O prime. In the case of rotation about a fixed point, n cap is a function of time also, because with the passage of time n cap changes, and in this first category n cap does not depend on time. Now if the body is rotated by an angle theta, the rigid body, if this is the angle of rotation d theta, so if we choose d theta as a vector, then it is n cap times d theta is the vector. This vector is directed along this n cap, and as a result, the ith particle whose position vector was Ri is now moved to Ri plus Dri. If we choose a sectional view, then this is the initial position and this is the final position. So this is the angle of rotation d theta. Due to this is going to the displacement of the ith particle. This is O prime, and this distance is R0I. It is the R0I is this much, this distance. Obviously, DRI is equal to d theta times Ri cap, because this arc length is this. You see that for a rigid body, if it is be rotated by an angle theta, the angular displacement is same for all the particles, but the linear displacements are different for different particles, because each particle rotates on the circumference of the circle, and the linear displacement depends on the radius of the circular path. If we differentiate this expression with respect to time, then we get linear velocity vi of the ith particle. This is omega, the angular velocity, times vector ri. This is the very familiar relation. And if we differentiate it once more with respect to time, we get the acceleration of the ith particle ai. If we differentiate d omega, this is dt of omega cos ri. So this is d omega dt cross ri plus omega cross dri dt. So we call it angular acceleration alpha times ri plus omega times vi. If we substitute vi by this relation, we get it alpha cross ri plus omega cos ri. If we decompose it, in terms of back curve rule, then we get this is omega this is the relation. So the relation between linear and angular quantities. So the relation is that for displacement dr is equal to d theta cos ri, and linear velocity vi is equal to omega cos ri, and acceleration is alpha cross Ri plus omega cross Vi. And we can substitute quantities in terms. Now we express these quantities in terms of axis of rotation, that is the instantaneous axis of rotation to be on the set side. So in terms of axis of rotation, d theta is equal to n cap d theta, omega is equal to n cap omega, and alpha is equal to n cap alpha. You see that all these three angular quantities are directed along the axis of rotation and so forth, angular momentum and torque. Now dri, if we write dri, the basic relation d theta cos r cap, this becomes n cap Ri d theta. If we look at what is the quantity n cap Ri, if this is the n cap direction, this is Ri. So n cap dri numerically is equal to this distance, di is equal to n cap times dri. So this is the perpendicular distance of a particle having position vector Ri from the axis of rotation. So it can be written in the other way around also. Now coming to V. Vi is equal to n omega cross Ri, this is the general relation, and this is omega Ni cross Ri. Again, Ni cross Ri is the distance of the point ith particle from the instantaneous axis of rotation. This one is alpha Ni cross Ri plus following. So we will first write the general relation. Alpha cross Ri plus omega cross Vi, which now comes out to be alpha n cross Ri from this part. And from this part, this is omega square n cross Ri. So this is alpha n cross Ri plus omega square. This is the expression of the angular quantities in terms of direction of axis of rotation. So this is the component, if we come this is the direction component of acceleration in the direction of the axis of rotation, and other parts represent the off-axis components. The situation becomes very simple or very convenient if we use the rotation to take place about z-axis. If we use z-axis as the axis of rotation, then d theta is equal to k cap d theta, omega is equal to k cap omega, and alpha is equal to k cap alpha. In which case we write this expression as DRI can be is written as, we can write it as k cap cross I cap xi plus j cap yi plus k cap zi times d theta, which comes out to be minus I cap yi plus j cap xi d theta. Yet another convenient way of writing is that if we write r is equal to rho I times rho I cap times j I times k cap, in which case this is k cross rho I times rho I cap plus j I times k cap d theta, and this part is 0 and this is phi part. K cross rho I is phi I cap, so this is rho I phi I cap d theta, where this rho I is the distance of the ith particle from the axis of rotation. That is, rho I is actually n cross Ri cap. So this, if you use cylindrical coordinate system, interpretation becomes easier. If we come to this relation, Vi, so Vi is equal to omega k cross I cap xi j cap yi k cap zi. This is equal to omega minus I cap yi plus j cap xi. And if we write it in terms of the cylindrical coordinates, so this is this part omega k cap cross rho I cap zi k cap, so this becomes omega rho I phi I cap. This is the magnitude of the linear velocity, and it is directed along the phi cap. Now coming to the acceleration part. Acceleration AI is in terms of components we write. This is alpha e cap cross I cap xi j cap yi plus k cap zi from this part, this term, plus omega, this is k cap omega cross vi for v, this is vi, for vi we write minus I cap yi plus j cap xi times omega, because if we write it in terms of Cartesian components, this is the expression. So from this part we get alpha minus I cap yi plus j cap xi, plus here we have, this is omega square, these two omega square, this is plus j cap yi, and this is k cross j. So k cross I is this is minus j cap and this is minus I cap. So the relation is, if we take the component of I cap I, the component of I cap is alpha yi times omega square xi, and the components of j cap is alpha xi minus omega square yi. This is the components, or if the rotation takes place about z axis, then this is the component acceleration. This expression looks to be a bit cumbersome, and we could have expressed it in a much better way if we write it in terms of cylindrical coordinate system. In cylindrical coordinate system, we derive this expression as, so you will see that this is the relation in Cartesian, this is cylindrical, this is Cartesian, this relation is in cylindrical, this is the relation in Cartesian, and we are going to have this relation in cylindrical coordinate system. So in cylindrical coordinate system, it is AI, so this is alpha Ri, so this is k cap alpha cross rho I cap plus zi k cap, this is for the first one, this one, plus k cap omega cross b, and you see that the b is this part, omega rho I phi I cap. So here we have this part goes and only this part survives, so this is alpha rho I phi I cap this is phi I cap, and we have this part. This is minus rho I cap, so this is minus rho I omega square rho I cap. So we see that this is the centripetal acceleration. This is the centripetal acceleration. The negative sign indicates that the acceleration acts towards the center of the radial circular path. So this is the position, and if it is this direction which is signified by this. So this is the radial part which is directed towards the center of the circle prime, and this is the tangential part of the acceleration. So this is the radial or centripetal acceleration, and this is the tangential acceleration. So that's about the relation that exists between rotational kinematical quantities with the corresponding linear quantities. In the next class, we shall address the dynamical aspect of rigid body. We shall start with the rotation of a rigid body about a fixed axis.